Hello again, guys. Welcome to part 3 of lecture 6 of our lecture series, Chemistry for Engineers. This section will be focused on electron configuration, ionization energy, as well as electron affinity. We can see how the concept of effective nuclear charge allows us to understand energy ordering of orbitals. The graph shows the probability of finding an electron as a function of distance from the nucleus of each subshell up to N3. It is obvious that there are substantial size differences between shells such that 1s is notably smaller than 2s, 2p, which in turn are smaller than 3s, 3p, 3d. The graph of radial probability function are shown for 4 hydrogen orbitals with n1, 2, and 3. The increase in orbital size with the increase in n is obvious. So this graph basically shows a decrease in orbital size where n increases. So the size of the orbit increases at lower energy level. The size of the orbit decreases at higher energy level. Compare the 2s and 2p wave function. Although the overall size of these orbitals are similar, the 2s wave function shows a small local maximum close to the nucleus. So this shows the actual increase in each energy levels and also the descending order in which the orbitals are filled. Each box represents one orbital and can contain a maximum of 2 electrons. There is one s orbital, 3p orbital, 5d orbital for each principal quantum level where an sp or d orbital can exist. And again, this basically shows the subshell where n1 can only occupy s1 or only exist as s1 subshell with only 2 electrons, and 2 can exist as 2s, 2b, and 3 can exist as 3s, 3p, 3d, and 4 can exist as 4s, 4p, 4d, 4f. And remember, for s, only 2 electrons, for p up to 6 electrons, for d up to 10 electrons, for f up to 14 electrons. So the 2s shows that there is a smaller maximum closer to the nucleus, which is why the 2p subshell basically came about, but there is no such feature appears in 2p wave function. This means that 2s electron has a greater probability of being found very close to the nucleus, and an electron closer to the nucleus will experience a larger effective nuclear charge. As a result, 2s orbital is lower in energy than 2p orbital. Similarly, the 3s orbitals on average interacts with a larger charge because of the probability it will be close to the nucleus, even though the first 2 lobes of the radial wave functions are small. This again shows the energy level and the subshells that are possible for each orbital. The Aufbau came from the German word to build. The process of deciding which orbital holds electron in an atom requires that we fill orbitals starting with the lowest energy level proceeding to the highest energy level. So you basically can write it like this, where you write from the different energy levels, 1, 2, 3, 4 energy level, and you can start with the first subshell, which is s subshell for each. Process of deciding which orbital holds electron in an atom requires that we fill orbitals starting from the lowest and proceeding to the highest energy level. So when you fill in the orbitals, you start from the energy levels first, so the first, second, third, fourth, fifth energy levels. In some way, this concept resembles constructing a building from ground up, and it is referred to as the Aufbau principle. So you start with the energy level, then you start with the subshell S, and this is the second energy level, and the subshell P, and the third energy level D, as well as the fourth energy level, and so on. And this is basically how you derive the electron configuration, for example, for boron. So boron has an atomic number of 5, and you start from the first energy level, the 1s energy level, 2 electrons, so it would be 1s2. Start with the second energy level, this holds up to 2 electron as well, so that would be 2s S2 followed by 2p subshell, which would hold the other one. So that would basically give us the 5 5, the atomic number of 5, which will give us the electron configuration for boron. The hydrogen atom has 1 electron and it occupies the 1s orbital. Helium has 2 electrons. Both can occupy 1s orbital as long as they are spin paired, so they'll have opposite spin, as you can see here. The lithium has 3 electrons. Only 2 can occupy the 1s orbital, and so 1 electron must go to the next lowest energy level, which is 2s. And a shortened way to design this orbital occupation is to write the orbital name followed by the subscript indicating the number of electrons in the orbital. Thus, lithium has electron configuration of 1s2s1. So you basically can shorten the electron configuration by writing the atom that has a very high orbital followed by whatever. Beryllium is the next element. Its atoms contain 4 electrons. The 2s orbital can also hold 2 electrons, so the 4th electron is paired. There is electron is placed there. It gives a configuration of 1s2s2. With 5 electrons, boron will also fully populate both 1s and 2s orbital, but we must account for an additional electron. The 5th electron goes into the next available orbital, 2p, to give 1s2, 2s2, 2p1. And these are the elements and the electron configuration for each. And as I said in the first lecture, the periodic table is in perfect order where you're actually counting by atomic number. So hydrogen is 1. The electron configuration would be 1s1 because up to 2 electrons can occupy the first subshell, but hydrogen only have 1, so it would be 1. Helium has an atomic number of 2, so this would be 1s2. Lithium is 3, so this would be 1s2, 2s1. Beryllium is 4, so this would be 1s2, 2s2, and that would be 4. Boron is 5, and as you can count, 5. If you're given the electron configuration of the atom, you can actually state the atomic number, because carbon, as you can see here, would be 2, 4, 6. Nitrogen would be 2, 4, 7. Oxygen would be 8, as you can see. Important thing about the anion and the cation is that if the atom is positively charged, or for example it exists in a 3+ state, you'll have to write the electron configuration and then you minus the 3. So you're basically doing the opposite. If it's a positively charged in 3+, then you minus 3. If it is negatively charged in -3, then you have to add 3 electrons. Upon reaching carbon, we're faced with a choice. There are 3 different 2p orbitals, all with equal energy. So 2 electrons could pair and occupy a single 2p orbital, or they could occupy 2 different p orbitals and 1 electron in each. The correct choice is motivated by the fact that all electrons are negatively charged particles. 2 negatively charged electrons should repel one another. So the most energetically favorable configuration would have them occupy separate orbitals where they can be further apart from each other. So this is the electron configuration of carbon. The concept is summarized in Hund's rule. This states that within a subshell, electron occupy orbitals. So whenever it's possible, the electrons occupy orbitals individually. One possible choice is to use diagrams with boxes representing orbitals, as you can see represented here. So this basically represents the electron in respective subshell as well as the orbitals for oxygen, fluorine, neon. Another option is to identify the individual orbitals with subscripts such as p, x, y, and z. Once we are familiar with the electron configuration, the simple notation of 1s2, 2s2, 2p2 for carbon will suffice. You basically can write it a lot of different ways in order to fully express the correct way of deriving the electron configuration. So knowing Hund's rule will allow whoever reads this configuration to envision the correct orbital occupation immediately, provided by the more detailed representation. You can start by writing the quantum number, the numbers, as well as the subshell in specific order. As soon as you know what the atomic number is, you basically can eliminate accordingly. This is the example problem 4. Sulfur may be an important element in emerging lighting technology. What is the electron configuration of a sulfur atom? Sulfur has 16 electrons, so we can place 2 in 1s, 2 in 2s, 6 in 2p, 2 in 3s, and 4 in 3p to get 16. The electron configuration is 1s2, 2s2, 2p6, 3s2, 3p4. So this is basically the electron configuration of sulfur. So you're given the atomic number, which is 16. So 1s can hold up to 2. That would be 1, 2, 3, 4, 5, 6, 7. And you know that these are all s subshell, which can occupy only 2, followed by the p subshell, which can only exist from 2 to 3, 4, 5, 6, 7, followed by the d subshell as well as the f subshell. So you already know that 1s can occupy 2, so we cross that off. 2s can occupy 2, so you cross off 2s. Starting from 2p to this direction, 2p can occupy 6, so you cross off 2p, and you still don't have 16 yet because that would give you 10. So you can start with 3s, cross off 3s. 3s would also be 2, so that would give you 12. So you're still not there yet. Starting with 3p, you would only need 4. So the configuration of sulfur would be 1s2, 2s2, 2p6, 3s2, 3p4. So this way of doing it might be easier because you're given the atomic number. You would just need to write the numbers out, the integer as well as the subshell s, p, d as well as f, and you create the configuration by a process of elimination from this direction. For the detailed configuration, we must consider how to contribute the 4 electron in 3p subshell. If we imagine placing the first 3 electron each in separate 3p orbit and then filling in one of the orbitals by adding the 4th electron. The spin presented like this. So 1s can only have 1 spin up, 1 down. 2s can only have 1 spin up, 1 down. 2p can admit up to 6 electron, 1 spin up, 1 down. If it's 3, then it would be all spin up. Because we have 6, so each have a spin up, down, up, down, up, down. 3s admits 2, so we also have the same. And 3p, as we said again, can occupy up to 6. So the first 2 will be 1 up, 1 down. The last 2 would be up. Most fluorescent bulbs are filled with argon gas, but some use krypton gas. The fact that these gases are chemically inert is important for their role in operation of the lamp. What are the electron configurations of these 2 elements? So I don't have to do this one again with you. The electron configuration for argon is simple. For krypton is simple. All you need to know is the atomic number for each. This is the atomic number for krypton. So these elements are chemically similar. Both are essentially inert precisely because they have familiar electron configuration. In each case, the last electron fills the p subshell. The correspondence between chemical inertness and a filled p subshell provides the motivation for a standard notion for electron configuration. So the important thing is they both have filled p subshell. More importantly, it introduces a very important concept that relates electric structure to chemical bonding. The electron in the outermost occupied shell gives rise to the chemical reactivity of an element. Electrons in filled lower shell will have little impact on an element's chemical properties. So basically, if the lower shells are filled, it's really not so significant because the chemical properties of the atom is dependent on the valence electron or the electrons on the outermost shell. The inner core, which lies close to the nucleus, are called core electrons that are not necessarily significant for chemical reactions. Core electrons can be represented by the atomic symbol of a rare gas element that has the corresponding electron configuration. Although the complete electron configuration for potassium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, the outermost 4s1 electron determines the chemical properties of potassium. We emphasize this fact by writing writing the configuration as argon 4s. It basically again simply means that it has the same configuration as argon, but the 4s shell is the outermost valent electron. Similarly, tin can be written as krypton 5s2 4d10 5p2. The electrons that are explicitly noted in this notation occupies orbitals that are further from the nucleus. Although it is appropriately descriptive to designate them as outer electrons, they are usually referred to as valence electron. The shape of the periodic table can be broken down into blocks according to the type of orbitals occupied by the highest energy electron in the ground state of each element. Alkali metals, alkali earth metals would be considered the S block, and these numbers indicate the highest energy levels. So the alkali metals and the alkali earth metals are the S block, or the main group element S block. And here we have the lanthanides and the actinides inserted as the F block. So the transition metals would constitute the D block. The main group element would be the P block. So the F block elements are usually broken out of the table and displayed separately at the bottom. So this basically breaks down the periodic table in shapes. Thus, all the elements in the section at the left edge of the table, shaded in the red, have the highest energy electron in an s orbital. All the elements in the section at the left edge of the table, shaded in red, have their highest energy electron in an s orbital. These are sometimes referred to as the s block. The green section at the far right of the table, which is the p block, according to the Aufbau principle, the last orbital occupied is a p orbital. The transition metals are d block, which we have here and here, and the lanthanides and the actinides make up the f block in yellow. The transition metals have their highest energy level in the d block as well as f block respectively. Because of this structure, we can use the periodic table to determine electron configuration for elements. A few exceptions arise mainly among the transition metals. We find the elements of interest in the periodic table and write its core electron using the shorthand notion with the previous rare gas element. Then we determine the valence electron by noting where the electron sits within its own period in the table. So you basically can use a shorthand notion where you can find the elements or the core electron using the shorthand notion, and then you can determine the valence electron. So you can start with the core and determine the valence electron. Use the periodic table to determine the electron configuration of tungsten, which is used in the filament of most incandescent lights. Use the rare gas element for the previous periods to abbreviate the core electrons. So here we have the atomic number of tungsten as 74. Xenon was used in this case with an electron configuration core of 5p. So the rest would be 6s, which is 2, 4f of 14, 5d of 4. And we use xenon because xenon has an atomic number of 54. So that would be at the 5p level. This would be followed by 6s2. So that would be 54 plus 2 plus 14. That would be 16 plus 4. That would be 20. So this would be 54 plus 20. And this is basically the shorthand version. So if you use the periodic table and you count, which would take a lot of time, then you'll get to xenon, which is 54, 55, 56, 57, 58, 59, 60. But remember that you'd also have to insert the lanthanide, which would actually give you the accurate number of 74. The rare gas element preceding tungsten is xenon. When counting the valence electron, don't forget the f block. So naturally, you would have to insert the f block. So it would be xenon 62. So xenon is 54, 62. That would be plus 2. 4f, which would be 14, can admit up to 14 electron. 5d, so that would be the remainder, and it would be 4. So this would be 70, and then this would be 4 that would be needed for a configuration of tungsten. Mercury is used in fluorescent fluorescent lamp as well as mercury vapor as vapor lamps. Use the periodic table to determine the electron configuration of mercury. So here again we use xenon because mercury is here with an atomic number of 80. So it's ideal to actually use the inert gas or the gases due to their high atomic number and create the configuration as a result. So that would be 1, 2, 3, 4, 5, 6, 7. So those, all of these would be S, 1s, followed by 2 would be 2p, 3, 4. So that would be p, followed by 3. This is D, 4, 5, and these are F. So we know 1s1 is 2, 2s, 4, B is 6, 6 plus 2, this would be 12, followed by 3p, which would be 6, so that would be 18, plus 2, 20, followed by 3d, followed by 4p, followed by 5s, followed by 4d, this would be 2, 4, 6, 8, 10, this would be 12 plus 6, 18 would give us 28. 3D is 10, basically gives you 38. So 4D would be 10, followed by 5P. And here, around here, we basically get to the configuration of xenon. So this would be 54 at this point, and mercury is 80. So the next would be 6S, which would be 2, followed by 4F, which would be 14. This would be followed by 4F, which is 14. So at this point, we're actually at 70. So we need 10. So if we extend this to 5D, that's where we would basically stop. And that would be the electron configuration for mercury. All halogens have electron configurations ending with NP5, where N is 2 for fluorine, 3 for chlorine, 4 for bromine, and 5 for iodine. The similarity in electron configuration leads to similarity in chemical behavior and electron, why different halogens can be used with similar results. So the important thing, as we mentioned before, are the configuration on the outermost or valent electron. The choice of specific halogen in a bulb can be adjusted to achieve desired design parameters, but all halogens behave in roughly the same way, enabling a combination of increased brightness and extend lifetime. So when you use the halogen with the incandescent light or the tungsten, you can see that the molecules synergize, which creates a longer duration for emitting photons due to the molecules interacting, and as a result produces a more reliable product. Using the understanding of orbitals and the atomic structure, it's possible to explain some of these periodic variation in greater detail. One important characteristic of atom is their size. The measurement of atomic size is sometimes complicated. The result of these measurements are summarized here. So the graph basically shows atomic radius as a function of atomic number. The different colors and data point symbol represent the different rows in the periodic table. The decrease in size from left to right across the periodic table is clearly seen. So the size of the atom decrease in this direction. So from the main group elements, the size of the atoms decreases, followed by the transition elements, which are seen here. The size are the radius in picometer. So the main group elements are around up to 50 picometer. The transition metals or elements are up to 150 in radius. The actinides are here. The actinides and the lanthanides are here. And most of these would represent these atoms here. As we go down a group, we observe an increase in atomic size. As we go across a period, we observe a decrease. An easy way to remember this trend is to draw what look like a XY coordinate axis at the bottom left of the periodic table, and an increase in either X or Y direction on the axis corresponds to the decrease decrease in the atomic size. There's an increase in radius here as it goes down for these elements especially, and there's a decrease in radius as they go across. So if you draw a line through this in this direction, the atomic size increases in this direction. The size of the atom is determined largely by its valence electrons because they occupy the outermost orbitals. Two factors are important. One, the shell in which the valence electrons are found. Two, the strength of the interaction between nucleus and the valence electron. As we go down a group in the table, the first of these factors is at work. So the valence electron, which is the outermost electron, determine the size. And as you can see, all the atoms with the largest or one valent electron tend to be larger. Helium would naturally be a bit larger as well, but from this direction down, these atoms with valent electron, very large valent electron, would be much smaller, or far more electrons on their outermost orbital would be much smaller. The size of the valence orbitals increase with n, so the size of the atom increases as we go down the periodic table. The trend in moving across a row is less intuitive. The distance between a valence electron and the nucleus will tend to be greater if there is a small effective nuclear charge. Well, this is basically just showing the atoms in terms of their atomic radius as well as the atomic numbers. So from this direction down, you can see that the largest would be cesium, followed by rubidium, potassium, sodium, lithium. So from this direction down, so the gases tend to be very small on average, as you can see. So from this direction, they increase in size. As we go across a period, we add electrons to the same subshell. These electrons do not shield each other very well, and the effective nuclear charge increases because each increment in atomic number adds a positively charged proton to the nucleus. The higher effective nuclear charge produces a stronger attraction between electrons and nucleus. So the valence electrons are drawn closer to the nucleus and the size of the atom decreases, as we mentioned before. And this is also another visual depiction of the sizes of the atom. And it's important to know that cesium, potassium are very large. Xenon is also relatively large, krypton as well as argon. These are relatively large, but in general, the gases tend to be really small. Using only the periodic table, rank the following elements in order of increase in size: iron, potassium, rubidium, sulfur, selenium. So sulfur and selenium are both in group 16. Because sulfur is above selenium, it will be smaller. Similarly, the position of rubidium and potassium in group 1 here tells us that potassium is smaller of the two. And as you can see, iron is right here. Potassium ion and selenium in fourth period is the rightmost of three, so it will be the smallest, followed by iron, then potassium. Because selenium is in the rightmost of the three, potassium and iron and selenium are in the fourth period. Because selenium is on the right most of the three others, it will be the smallest, followed by iron, then potassium, because we're increasing in size in this direction. So putting all of these factors together gives us sulfur, selenium, iron, potassium, rubidium. Another property of atoms that plays a role in the way they interact in forming chemical bonds is the ease with which they lose electrons. This property, called ionization energy, can be measured by an experiment similar to that we described earlier for the photoelectric effect. The ionization energy is defined as the amount of energy we would have to supply to induce the following equation: X gas produces X plus gas minus electron. So ionization energy is the energy needed to remove an electron from an atom. Electron affinity is the energy change when 1 mole of electron is added to 1 mole of gaseous atom to form 1 mole of gaseous ion. So ionization energy tells you the amount of energy that is required to remove remove an electron, while electron affinity tells you the amount of energy that is required to add an electron. To be more precise, the energy required for this reaction is the first ionization energy. The energy needed to remove an additional electron from the X gas cation, forming X2 plus, would be the second ionization energy, and so on. The ionization energy can be represented as this. X1 gas plus energy basically gives you X2 plus gas plus electron minus X2 plus gas plus energy gives you X3 plus gas plus electron minus more energy required to remove the second electron and still more energy required to remove the third electron. The graph shows the first ionization energy in joules per mole versus atomic number for the first 38 elements in the periodic table. Insert in the upper right emphasizes the general periodic trends. Ionization energy increases from left to right and bottom to top in the periodic table. The ionization energy required in kilojoules per mole for hydrogen to helium, to lithium to beryllium, to boron to carbon, to nitrogen to oxygen, fluorine to neon, to sodium to magnesium, aluminum to silicon, fluoride to argon, potassium to calcium, scandium to titanium, iron to nickel, nickel to zinc. Connection between periodicity and atomic structure can be seen by looking at the way ionization energies varies across periods and within groups of the table. With the atomic size that as we proceed across the period, the effective nuclear charge increases. Not surprising, the ionization energy also generally increases across a period. As we move down a group, the valence electron occupy larger and larger orbits. So from hydrogen to helium, we could have seen on the chart that there was increased ionization energy. From lithium to beryllium, there's increased ionization energy. From boron to carbon to nitrogen to oxygen as well. But in this direction, there is a decrease in ionization energy. As the valence electron move further from the nucleus, they become easier to remove. So ionization energy decreases as we move down a column in the periodic table. As we proceed up and down and towards the right in the periodic table, ionization energy increases. In this case, the valence electrons are further apart. Here we have one valence electron, two valence electron, one valence electron as well, two valence electron. Boron in this case would have one valence electron. So basically it means that the less valence electron are on the outermost shell, the ionization energy increases. The more valence electron on the outermost shell, the ionization energy decreases. Additional clues about the atomic structure are revealed by the exception to the trends in ionization energy. We see that from nitrogen to oxygen, there is a slight decrease in ionization energy rather than an increase expected based on the periodic trends. This observation can be rationalized by considering electron pairing. So when nitrogen is paired to oxygen and when beryllium is paired to boron, you can see that there is a slight decrease in ionization energy. So in terms of electron configuration and bonding or atomic bonds, nitrogen has a half-filled p subshell with one electron in the 2p orbital. To accommodate its p4 configuration, oxygen must pair two electrons in one of the 2p orbitals. Removing one electron therefore leaves only unpaired electrons in all three 2p orbitals. So the p orbital consists of 3 electrons, and as you should remember, the p orbital can hold up to 6. So in order for nitrogen to pair with oxygen, oxygen must pair 2 electrons in one of the 2p orbitals. So oxygen has 4 in its p subshell and has to pair 2 in the p orbital of nitrogen. So it basically removes 1 electron, therefore leaving only unpaired electron in all 3 2p orbitals. So oxygen has 4, nitrogen has 3, a maximum of 6 can hold. So 1 is removed, leaving only unpaired electrons. Such a change leads to notably less electron repulsion, enough so that the ionization ionization energy of oxygen is lower than that of nitrogen. Similar expectation to the trends are seen for sulfur in the third period and selenium in the fourth period. So the selenium will pair where the 3p from sulfur and the 4p from selenium will cause the removal of 2 electrons. Ionization energy increases as we go up to the right in the periodic table. From our list of elements, all but fluorine have in the fourth period, so we expect their ionization energies to increase from the left to the right. Finally, fluorine lies above bromine in group 17, so it will have the largest ionization energy. This gives us the requested order. So from the left to the right, potassium, gallium, selenium, bromine have increasing ionization energy in this direction, with the exception of fluorine. So fluorine will have the highest ionization energy, and as we can see here, the ionization energy decreases in this direction. We can also gain insight into the atomic structure by looking at successive ionization energies. For sodium, the first ionization energy is among the lowest, but for the second, it is much larger than that of the neutral atom. For magnesium, the situation is quite different. The second ionization energy is larger than the first because the effective nuclear charge experienced by a valence electron is larger in the ion than in the neutral atom. So this basically shows the ionization energy in kilojoules per mole in the specific order. The more dramatic change in ionization energy lies between the second and the third ionization. The point at which the large jump occurs for elements is highlighted throughout the table. In each case, the largest increase in ionization energy occurs when an electron is removed from a completely filled p subshell. When all the electrons are removed from a subshell that is filled, which is with 6 electrons, that's when you have the largest ionization energy. So when an electron is removed from a completely filled subshell, and you know the p subshell can hold up to 6 electrons, that's when you have the largest jump in ionization energy. So from this observation, we can see the usual stability for filled p subshell, and we can begin to appreciate why noble gases elements are so unreactive. Filled subshell of electrons are difficult to break up. So when you take off an electron off a full subshell, it kind of causes a jump in the ionization energy. So in essence, the subshell or the valence electron also determines the stability. So the first 4 ionization energy levels, all in kilojoules per mole for the elements of the first 3 periods. These ionization energy with values shown is shaded in the cell with bowl involve the removing last electron from the particular shell. Further, ionization energy requires moving an electron from a more stable filled shell, and this leads to a large increase in ionization energy. So this basically shows the ionization energy required for removal of the N3 and 4 subshell at 6,000 joules per mole, 4,300 joules per mole for silicon, as opposed to 495 for sodium at the first energy level. Ionization energy is defined as the energy required to remove an electron from an atom, forming a positively charged cation. But we also know that some atoms will routinely pick up an electron to form a negatively charged anion, and this is basically where electron affinity comes in. The electron affinity of an element is defined as the energy released when an electron is added to an isolated gaseous atom to form a gaseous anion or a negative ion. So the gas plus electron gives you an anion. A decrease in electron affinity to this direction and an increase in affinity toward this direction. We can define a property property called electron affinity as the amount of energy we would have to supply to induce this reaction. So how much energy is required to make the atom become negatively charged or lose an electron? Removing an electron from a neutral atom always requires an input of energy because the atom will not simply eject electron on its own. Ionization energies are always positive. So if you add an electron, it's reflected as negative. If you remove an electron, it's reflected as positive. So chloride gas minus an electron shows that 1251 kilojoules per moles of energy was absorbed. Chloride anion in the form of gas release minus 349 kilojoules per mole. So it basically shows that energy was utilized for the chloride atom to become a chloride anion. But electron affinity values can be either positive or negative. So only if the resulting anion is stable, then it can be positive. The energy will actually be released as the electron is added. But our definition of electron affinity says it is the amount of energy. Affinity values are negative. So the affinity increases to this direction while there's the opposite for the electron ionization energy. We must be supplied to form the anion. If energy is being released, we must say that we must supply a negative amount of energy, so the electron affinity value will be negative. If the electron affinity is positive, that means that the anion formed is not stable. In this case, we would need to supply energy to force the atom to accept the electron, most electron affinity. So you have first order electron affinity as well as second order electron affinity. So where the oxygen in the form of gas obtains an electron to become a monovalent oxygen ion, minus 42 kilojoules of moles was required. In the second electron affinity, this monovalent oxygen ion gains an electron to become oxide gas, where energy is absorbed at 844 kilojoules per mole. We define the signs in this way because it is consistent with the convention usually followed when discussing energy in chemistry, physics, and engineering. Energy added to an atom is positive. Energy released by an atom is negative. Electron affinity values display periodic trends based on electron configuration, but like the other properties, the most immediate conclusion might be that electron affinity values vary more erratically than ionization energies. So it should be evident from the figure that we move from bottom to top or from left to right in the periodic table, the electron affinity tends to become more negative. So as you move from bottom to top and from left to right, the electron affinity becomes more negative. From bottom to top, from left to right, it becomes more negative. So here we have fluorine to oxygen. Nitrogen does not have a negative electron affinity because adding an electron would force the pairing of electron in a p orbital, a process that increases the electron repulsion. So because you have one up, one down, so for the 2p subshell, it easily admits 3 electrons. So this basically forces the pairing, natural pairing of the electrons. Similarly, the developments in chemistry have helped identify new phosphomolecules that drove improvement in fluorescent lamps. Today, new technology rely heavily on the modern light, such as light-emitting diodes or LED and lasers. You can almost certainly find light-emitting diodes in many of the appliances you use every day. The power indicators on everything from cell phones, TV to displays on many digital alarm clocks and microwave ovens are just a few examples of common use of LEDs. One characteristic of LEDs, each LED light emits light of a particular color. Although you can buy colored incandescent bulb, they rely on some sort of filter coated on the surface of the bulb. The filament still emits white light, so the color filter greatly reduces the efficacy of the bulb. In a LED, light light emitted is usually monochromatic, which means that it is restricted to a single wavelength or color, as we shown before in our first lecture. So LED provides an easy way to produce colored light, and that's one reason why they are so widely used as indicators on electronic devices. Another important contrast between an LED and a small incandescent bulb is durability. Light bulbs break or burn out, but LED lasts almost indefinitely under normal conditions. We've seen that bulbs burn out because their filaments gradually break down at high operating temperatures needed to produce light. An LED does not require a high operating temperature. It functions as long as small electric currents flow through it. This gives the LED a long useful lifetime and also reduces the amount of power consumed and heat given off, both of which can be important design consideration in modern electronics. Because they lose very little energy as heat, LED can operate at very high efficacy, converting nearly all of the input energy into light. This is especially important for small portable devices such as cell phones, MP3 players, where battery life is a major consideration. So the standard design of an LED is extremely simple. Metallic leads allow current to pass through a small piece of semiconductor material, which then emits light. A plastic enclosure serves as both a lens and a case for the device. The color of the light emitted is directed by chemical composition of the semiconductor. Because LED are superior to incandescent light, its efficacy and durability, they are now routinely used in traffic lights. This is basically just showing the semiconductor metals, and remember that we said that the electricity moves from the N layer to the P layer, it falls in the hole and emits the light as a result of interacting with the semiconductor. Lasers share some traits with LED. They produce monochromatic light, and the wavelength of that light depends on the specific properties of the laser. Light emitted by a laser is highly directional and emerges as very well defined beams. You also certainly see the beam is generally not even visible from the side because all of the light is traveling in the same direction. Laser light is also coherent, which means that all of its waves are perfectly in phase and go through maxima and minima together. Many varieties of laser are known, ranging from small devices used in DVD players, laser printer, supermarket price scanners, to very high powered system used in industrial machines. The invention of laser is a direct result of the emergence of quantum mechanical model of the atom. Laser light is emitted as atom or molecules go from higher energy level down to a lower energy level, just as we saw in atomic spectra. So every laser design is ultimately based on a detailed understanding of energy levels available to atoms or molecules in what we call laser medium. The operation of a laser generally relies on a phenomenon called stimulated emission, which becomes important when the population of one energy level becomes greater than the population energy of a lower energy level. Many of the most common lasers like DVD players are solid state devices in which the population immersion is established for electrons in a solid. As you can see, this is a helium neon laser in which there is helium. The helium becomes excited at energy level 2, and the E3, which collides with the neon atoms in the ground state or the ground level. Neon are then excited to the level of E5 and E6. Then helium atoms comes back to the ground state. So this is a gas reservoir where the helium and the neon interact. And of course the glass metal is always protective. The electricity has to be supplied to excite the gases, similar to fluorescent lights. The primary engineering challenges in designing a laser are to identify a medium that can emit the desired wavelength of light, and then to devise a way to establish and maintain the population inversion. So understanding of the energy levels involved are clearly essential. Liquid crystal display, or LCD, is a new lighting technology that emerged in the 21st century. This connection between chemistry and engineering continues to play a major role. Recent improvement in liquid crystal display use in panel computer monitors are due to pair of the development of new new chemical compounds whose light absorbing properties are tailored for the task. So this is basically an example of what a liquid crystal display looks like. A flat panel display does not really emit light directly, but basically uses a backlight reflector to produce images in colors or monochrome. Also have organic light emitting diodes, which is also relatively new. And this marks the end of part 3 of lecture 6. Hopefully this was very informative, and I'll see you for the next lecture.